Good morning. Walter Grayman. I'll be moderating this webinar, our 10th in a series put on by the Premise Plumbing Modeling Task Committee of EWRI. Our webinar today is on information management and modeling of premise plumbing systems. And you can see the agenda here. Unfortunately, Phil Woolhouse will not be able to join us from Australia. It's middle of the night and he's having some health issues, but we will go ahead. We have 4 speakers. So to start off today, our first speaker is Steve Butler, who is with Autodesk in England, and he's going to give us an overview of building information systems, BIM. Steve.
Okay, so good morning, everyone, and thank you for the opportunity to present to you today, providing an overview of building information modeling, BIM, for premise plumbing or for piping generally, but also applicable to more broader disciplines across MEP. My name is Steve Butler, as Walter said. I work for Autodesk and I'm responsible for our MEP business line. So I have about, I think, 20 minutes to present today, and I understand that it's a fairly mixed audience. I understood that some people might be using BIM technology and processes every day and are very familiar with them. Others maybe know the term or are aware of it, but are not maybe actively engaged. So I'm going to start by just explaining the sort of core principles and concepts, and then we'll look at how people are using the technology today, and then a little bit of a look at sort of where it's headed and how people are sort of moving that technology forward. So it's probably not going to be as deeply technical as you're used to, or as the other presenters are going to present on, but it's intended to be really a focus around building information modeling. So with that said, I thought it would be interesting to start by, excuse me, there we go, looking back a little bit at the history of our industry and how technology has really disrupted it and changed it quite significantly. So some of you may remember, as I do, around about 35, 40 years ago, this slide's a couple of years out of date probably, we moved from the drawing boards, or we started to CAD, to electronic drafting essentially, which is a significant moment because we automated processes quite considerably. We were able to generate documents much quicker, and it also gave us an opportunity to standardize on those documents and provide better quality and consistency. We then moved about sort of 15 to 18 years ago, again, depending on sort of maybe where you are in the world, to BIM. So it's not a new concept or technology at all. And that really changed things quite considerably. So while you could do 3D coordination modeling in CAD, and that helped in terms of making sure we weren't sort of making the same, historical, making the same mistakes on the construction site. What happened with BIM was it added a level of intelligence, but more importantly, it added collaboration. It brought the 3 disciplines together in many cases. It allowed people to collaborate in different kinds of ways. So often people say, well, what's the big deal? I was always able to build my buildings with CAD. But what BIM brought was really that higher level of collaboration. And that continues still on as we now start to move into the next phase of BIM, which is the era of connection, which is BIM plus the cloud. So with cloud, we now have infinitely more processing capabilities. So we can do a lot more, we can do it quicker, and we can start to explore different tasks and activities, as I'll talk about as I go through my presentation. So that's really sort of opened up collaboration in a completely different way, which we've seen through the pandemic over the last year or so. So what is BIM? So as you see from this video, we've got some basins, a urinal, some toilets. These are intelligent objects that understand, what connects to them. So, whether it's a soil pipe, whether it's a hot or cold water pipe, they understand what should connect to it and how. So you can't connect pipes to ducts and ducts to conduits. That level of sort of understanding of behavior and of relationship and fit, form and function is what we get from BIM. Grills know that they live in the ceiling, toilets hang off walls. And so that really changes how we start to interact with the model. And it goes beyond just being a documentation tool. You can see that the same model can be used in many representations. So it can be seen in plan view, in section elevation. There's no producing those separately and trying to keep them in sync. You just take a different view on the model, and that becomes, you know, what your section or your elevation is instantly updated whenever a change is made. This level of collaboration means that if the architect changes maybe the depth of a ceiling void, then you can instantly, as a structural engineer or an MEP engineer, you can see, you know, what impact that's going to have on your model. As I said before, really, in BIM, a true BIM platform really should be multidisciplined and support, you know, obviously each of those disciplines in supporting the collaboration process. And this model that we're producing, which, as you can see, we can show in different ways with different line weights, whether it's single line, as you see here, double line, or whatever, just by filtering out your view on the model, can also be used for other things. So typically, it's become very much a coordination management tool, document management tool, document production tool. But it's also used in visualizations, as I know you're aware. But increasingly, it's being used for analysis and design. So if we look at, you know, the big differences between CAD and BIM, looking on the right-hand side of this sort of slide first, we can see building information modeling is enabling the AEC industry really to transform. And it's because it's this integrated and collaborative process. It's also important for companies to remember that it's a process transition. It's a cultural shift from going from even 3D CAD to BIM, because you are beginning to interact with the model in different ways, and you're using information and data to drive outputs and decision making. And that's really one of its core tenets. Greater insight, you know, therefore, for all stakeholders on the project, and improved communication. So what it isn't is another CAD tool. So it shouldn't be thought of being, you know, the CAD department's new tool. It's actually part of many companies' business digitalization transformation plans. And a lot of it in the AC industry, for those firms, it's at the core of the beginning of that transition. It's not just a drafting tool or a documentation tool, and it's neither something that one company should do. Whilst it can be lonely BIM, if you like, something that one company does, it works better when every company is working collaboratively on a model. So as we see here, we're trying to go from sort of the historical sort of chaos, if you like, of throwing things over the wall, throwing a PDF over the wall, throwing drawings, prints, plots, you know, importing, exporting through, you know, multiple different applications, disparate applications, which means that we don't always know that we're looking at the right, most up-to-date piece of information. We don't know that, you know, if something changes, we can be slow to respond. So we want to move to what we see on the right-hand side here, which is more organization and collaboration, where we're all working on this kind of single model authoring tool, a common data environment. So we're shifting it really, as we're seeing in industry, especially as engineers start to use more BIM tools, from this sort of old-fashioned way of, as I say, using multiple different analog and digital tools, many of them disconnected, like engineers, from the BIM process, producing these sort of data silos where everything is also very much locked in. It's not open and exposed, and very much a black box in some cases. And the focus has been on documentation rather than optimization. So as we move towards more integrated BIM processes, we see that they also come you know, with application programming interfaces. They're more open, they're more extensible, and therefore they have a number of valid or a number of benefits. So increased quality and consistency is one of them, but increasingly the focus is becoming more on outcomes, and outcome-driven design is being enabled by outcome-driven modeling and analysis. For those that have moved to BIM, these are some of the benefits or return on investment that companies are seeing. This is from Dodge, but there's many reports out there, and it just talks to some of the things that people are getting in return for that investment, which is, you know, improved communication, less iterations, you know, less impact of design changes. But the other thing that increasingly BIM's doing is for companies is it's helping them to diversify services. So we're seeing at this moment in time, for example, a lot of companies that maybe have not done sustainability energy analysis or anything like that, you know, they would have exported that kind of work. As it becomes increasingly more important for them to do that, BIM is enabling them to take on those services internally. CFD is another one, particularly in light of COVID. We're seeing a lot more people use BIM to explore other technologies and other capabilities digitally. But it's fair to say, I think that, you know, most people still use BIM primarily for coordination, and you can see the results here. What it's doing is giving us more confidence in being able to design things up front and deliver, with some degree of certainty on site. It's also enabling things like off-site prefabrication, modular prefabrication, and so on, which I'll talk about a little bit in a moment. But when it comes to coordination, it's gone beyond just being 3D. We've now got tools that will actually help you overcome clashes, that will help you route around obstacles potentially. And so the tools are becoming increasingly more sophisticated. And depending on where you are in the world, the certain standards, one of them being levels of development or LOD, are starting to emerge, and receiving to some extent greater or lesser adoption, depending, as I say, on where you are and your level of BIM maturity. But what that's enabling us to do, or project stakeholders to do, is to understand where a model is, not just in terms of its graphics and what we could expect to see in that model, but in terms of its information. So very early on, sort of concept design stage, or early sort of late concept design stage, LOD 200 models, have very generic elements in them that are just grabbing space, and then associated information that's needed to support that sort of phase of the design. And then as it gets increasingly more detailed and maybe passes from design to contractor, we start seeing the models being enriched. And the goal really is to not have a design model, throw that away, and the contractor then starts with something else, which has historically been the case. The idea is to move the technology forward and add levels of information as they become available. So as you get to sort of an LOD 400 stage, you've got a model that contains enough information to support the detailing phases. You can export that model for fabrication. We can now do direct digital fabrication from BIM to support estimating, bidding, procuring, those kinds of things, as well as assembly of site modular and so on and so forth. So it's becoming increasingly more standardized and increasingly more valuable, therefore. So we're also seeing a number of engineers moving into BIM, as I said earlier, and they're starting to use the tools to do early stage design. This is an example from Europe, so I apologize. But historically, what you had to do was literally model all these fan coil units up before you could begin to size the system. But with recent enhancements, we're able now to do these virtual sort of connections where we can begin to size sort of primary runs to actually start to grab space and get some sort of early understanding of the size of the system and the capacity and so on and so forth. And that, as we get into detailed design, this is TME engineering from the US, we can start looking at sort of sizing our systems using more sophisticated tools and doing sort of hydraulic pipe sizing as you see here. And over the years, what's happened is that the ability to handle more complex pipe systems has increased, as well as the ability to handle larger and more complicated models. So what that's enabled engineers to do is start interacting with the model in a very different kind of way. So rather than spending all your time trying to model and then coordinate, and that being seen very much as the technician or the designer's role, now engineers are using it to help them design systems, but also overcome problems. Because you can actually do things smarter, you can start optioneering, looking at sort of what copper versus PVC plastic or whatever it is that systems you're using. You can start doing comparative analysis and other things like that, whereas you could never have done that before. We're also able, because of the technology enhancing, we're able to sort of drill down into more specific areas, whereas we might have sized for the worst case scenario historically. Now we have the capacity and ability to actually size different scenarios that we have throughout the building. However, as sophisticated these tools are becoming, they aren't, I would say, there yet, and so we do rely heavily, the industry that is, on third-party solutions as well. This is just a couple of third-party solutions that are available that drill down into specific areas, and typically we see plumbing being one of those areas. To do more sophisticated plumbing than is capable of some of the tools today. Fire sprinklers, another area. So you shouldn't ignore that. Part of the use of BIM technology is potentially using third-party solutions. This is an example of the model being used in the cloud. I mentioned earlier that the cloud is really changing things. This notion of being connected now, teams being connected, and what you're seeing here is a model that's been uploaded that we can then start to analyze in new and different kinds of ways. So on the right-hand side, you see here we can dig into the pipe system, how many pipes there are, how many fittings there are, etc., etc. So we can start to use the geographic information, as well as the geometry, as well as the actual data that's in the model, to drive and support different processes, be that things like estimated procurement. We've even got examples of people using scenarios like this in the cloud to drive things like pipe cutting, tiger stop machines, and things like that. As you get more down in sort of the project, and you start moving from designer to contractor and into sort of the detailing phase, as we call it, we can see that, again, BIM is helping to support contractors. In this example on the right hand side, you're seeing a manufacturer's library of real world content, and that content, that database of content, actually provides information on how much it costs, how each element costs, how much it weighs, what material it is, how long it takes to install. So labor rates, different types of labor rates, skilled versus apprentice, whatever. Increasingly, they're also supporting productivity tools, so going above and beyond what standard BIM can do to sort of focus on specific types of disciplines or specific activities. And then supporting sort of downstream things like spool diagramming and using that to drive shop-based activities, as you see here in this video. And again, helping to increase the ability and sophistication of delivering documentation at the end of the day, which you can share with other project stakeholders, as we see here. And this is helping companies like Mechanical Inc., which you see in this video, do just that, to perform off-site prefabrication, which is becoming increasingly popular in the US. They use it for off-site coordination meetings, on-site coordination meetings, doing it to drive different machinery, etc., etc. So it's becoming increasingly more connected. So you're using the model right up front from concept design stage, taking the architect's model to do early stage analysis, then doing all this plumbing and piping sizing throughout the sort of design phase, detailing it with the contractor, and then being able to push that out to either do the estimated procurement or variations analysis as we go through the project, and then also to push out digital manufacturing. The technology is also enabling the construction site or people in the field to communicate that with the office. So this is Andy Eager doing just that, using the cloud and BIM to actually be able to look at the same model and the same documentation that is being produced in the field. And the reason I highlight that is very often people are looking at the wrong revisions of drawings and not necessarily having to hand the right and most accurate information. So they use the technology to get access to it. They also use it to communicate back with the office if there's a problem. They can also use this technology to support the commissioning stages, so QA/QC in the field once things have been installed. So it's becoming increasingly more connected, increasingly more sophisticated, and increasingly bringing more and more stakeholders into the process. Something we shouldn't ignore either, which is becoming very popular, is laser scanning. This is just a simple example of how, an as-built, sort of as installed, I should say, sort of laser scan can be used to actually support the modeling process. That's one aspect of laser scanning that people have used, and it makes a lot of sense when you don't have accurate documents, when you don't trust the documents for an existing building, when you need to do a refurb project. The other area where this is being used increasingly is to monitor what's been installed that day. So you can actually start to look at, earned value. You can see what's been installed, so you can therefore invoice. And so there's lots of different ways that this type of technology is being used by companies around the world. Other companies are taking the technology still further. This isn't prevalent, by all means. This is just sort of people trialing different things, and some being more, sophisticated and more, achieving more benefits than others at this stage. So, but it's interesting to look at. This is a company in Europe where you can see they're using, augmented reality and the HoloLens in place of paper documentation to actually help them set out and assemble pipes in precast for sumps, as you see here. So for underfloor heating, it looks like a pretty sophisticated approach. And actually, I've been to this factory and I've seen them doing this, so it wasn't actually a gimmick in this case. So we'll see where this goes in the future. So I wanted to close with just taking a quick look at sort of BIM adoption. It's increasing around the world with release of the ISO standard 19650, which came out in the UK off the PAS that preceded it. So we're seeing a lot of sort of standards and guidelines. Not always standards, not always mandates, but standards, mandates, and guidelines in different parts of the world. The US doesn't have a government, as you know, sort of mandate, but the UK does, as does Korea, as does Singapore. And so people in countries are at different levels of BIM maturity, but it's definitely improving, and it's definitely being adopted rapidly. Japan was the most recent one to come on board in terms of adopting a standard. And you can see some of the countries that are sort of up and coming. So if we look at penetration, the green obviously being, and the darker green, so it's sort of more sophisticated, we can see that, you know, those high BIM adoption markets are North America, Northern Europe, and Australia and New Zealand. So it's certainly gathering momentum as people start to see that return on investment. So I think I'm a couple of seconds over, but apologies for that. That was all I had to present for you today. Back to you, Walter.
Steve, thank you very much. Excellent overview. And for us that are not familiar with BIM, it was a good summary. We're going to move a little bit from BIM into the modeling standpoint. And Tom Walsky, who is with Bentley Systems, is going to talk about hydraulic models, BIM, and other stuff. Steve, or Tom, sorry.
Yes. Thank you, Walter. Yeah, originally Walter asked me to talk about BIM, but with Steve coming on board as one of the speakers, I really downplayed that side of my talk, and I'm talking more about the other stuff. Last month's session, we talked a lot about premise plumbing from the inside and those decisions, and that's not where my background is. I'm coming at it from the water distribution system side, working with service lines and laterals and fire sprinkler systems. So I'm talking mostly today about the other stuff that wasn't covered in last month's presentation. Okay, so we'll move now into what we talked about last month is sizing the pipes, and that's all based on what I refer to as the law of conservation of fixture values, which is kind of not really part of physics, but this is the way pipe sizing is done. This is what last month's talk was about. And I'm going to be talking about hydraulic models, which are based on conservation of mass, where, you know, when you add up two flows, they add up to be equal, as opposed to fixture unit methods, which decrease the flows a little bit as you go downstream because of the probability of multiple fixtures being run at the same time. So we have two really different approaches. So this month, we're going to be talking about conservation of mass, and we're not going to mention the Hunter curve anymore, which was one of the main topics of last month's talk. Okay, so what do hydraulic models do? Or what do you have to give it? Well, the things on the left column are the items that you have to provide as input to run a hydraulic model of a premise plumbing system. And what do you get out when you put all that in? And most of that information is available in your construction drawings, your BIM, CAD, whatever it is. Those things are there for almost everything, except possibly you got to specify target velocity and maybe some pipe roughness information. But most of that stuff you already have at your fingertips. And what you get out of this is what the flow is in every element, what the diameter is, what the actual velocity is, what the head loss, hydraulic grade pressure. And we can do this for every pipe and junction and every time step. So it gives you the ability to simulate what's going on and create a digital twin of your system. And so this is where we're advancing as far as hydraulic modeling, what you put in and what you get out of a hydraulic model. And there's a lot of use cases. The most important ones we can do very easily right out of the box right now are flow, velocity, pressure, water age, and things of that sort. And with the right coefficients, you could do disinfection decay. But there's a lot more things that are coming up that are getting more attention: nitrification, microbial regrowth, and just any kind of multi-species analysis. But these really require a lot more input, a lot more stuff. Trying to specify an MSX model is not something the average engineer can do right out of the box. It takes a few experts to do it. And what you get out of these things then are the ability to simulate the system over time, incorporate process models of microbial regrowth, looking at the effects of storage tank and pumping, and then getting some things I'm going to talk about a bit today are things like laterals, meters, and backflow, and how they affect things. Now, one of the key things that make hydraulic modeling in a building different and more difficult than hydraulic modeling of the water distribution system is the nature of the water demands, because we can use a fairly smooth curve of demand versus time, but in premise plumbing, you can't really do that. The use of the water fixtures in a building is much more pulse oriented. Steve Buchberger has been in some of these sessions. I didn't see him on the list today of being here, but he developed a really good theory in Poisson rectangular pulse modeling, which is a lot like what we run into in rainfall runoff modeling of characterizing water use in buildings according to the intensity, duration, and frequency. And what I'm showing there are basically for any fixture, you know what the intensity is roughly, and you know the duration of how long someone's going to run that when they turn on a shower, when they flush a toilet, when they turn on a washing machine. The tougher one is the frequency, because the first two are kind of constants for a given fixture. The frequency of use, though, is a function of time of day. And that becomes a little bit harder to model. Like, how do you specify this to the standard hydraulic model of the system? But this is, the kind of modeling that the extra step you got to go to from a regular water distribution model into a premise plumbing model is being able to do this. And Miriam Bloker's work over in the Netherlands is a good example of some of those things that you can do along these lines. So what we saw last month was this example problem where you looked at a critical path and you would design the critical path based on fixture units, and then everything else would kind of follow off of this critical path. And that's kind of the way things are done nowadays, and that's not wrong or anything like that, but there's more you can do with combining this type of fixture unit approach with the hydraulic model. So let's get into some of the more detailed issues that come up when you're doing this type of analysis. One of the big things that struck me as I moved from water distribution modeling into premise modeling is that the internal diameter is not the nominal diameter. In big pipes, you get a very small error if you're using the nominal diameter as the actual, unless you use an HDPE pipe. But for the most part, then you can get by with that. But when you have these small pipes, the differences between the internal diameter and the nominal diameter are huge. And here's an example of comparing PEX and copper, where copper, for the same nominal diameter, you get about 40% more cross-sectional area. That's really a big thing. And you've got to be very careful when you're doing building plumbing. You can track the property of the pipe by its nominal diameter. But if you're doing hydraulic calculations, you better be using the actual internal diameter, because you can be pretty far off in the velocities and flows, travel time, and water age if you're not careful with this sort of thing. Now, how we do the modeling right now in water gems, which in EPANET and other similar kind of hydraulic models, if you just want to take a standard water distribution model and apply it in buildings, is they tend to be based on a two-dimensional view of the world, because that's the way water distribution systems are. So you can do some tricks, though, as I've showed in the talk I gave about a year ago in one of these sessions, where you can take them and lay out each floor with the plumbing in it and do simulations of it. And this is just, you take each floor and you couple them by the riser pipe going up through the building. And what you can do then are watch what's happening. You can run these animations where every time somebody opens up a faucet, the colors change and it shows the path the water takes. And you can do some really cool things in water age and such. And you can do all sorts of graphs. Here's a building where at night the pressures are pretty constant because nobody's in the office building. But during the day, you can watch the pressure fluctuations. And the bottom floor in red has the highest pressures. While you get up to the third floor of the building, you get a lot more pressures because of the elevation difference. We can also do things like tracking water age. Here's that same building that during the day you see, as soon as somebody turns on a faucet, the water age drops at that particular location in the system. While at night, when there's nobody in the building, the water age just ages as you'd expect. It gets 1 hour older every hour. And we could track this thing at multiple outlets inside the system. One of the things that you see in some buildings are rooftop water tanks. And you can watch how these affect water age. You can track how the tank fills and drains during the course of a day. And you can just look at the usage patterns. And so this is very useful because water age tends to be one of the critical things that we're studying as far as decay of water quality, because it's a lot easier than doing chlorine or some other real parameters. So we use that as a very common surrogate throughout the work that we do. Now, so what does this mean in terms of how you actually do the work? And this is, as we saw in the previous talk, what you start from. You start from some type of drawing of the building. And now you want to figure out how big those pipes should be. You know roughly where they are. and or almost exactly where they are, I should say, in 3 dimensions. But then how do you work with this? So I have a view of this. It's pretty similar to what Steve said, but just a little bit different. You know, everybody has their own little view of how CAD, BIM, and digital twins tie together. In hydraulic model of the distribution system, we start usually from GIS, and you don't really have a GIS of a building. So what's there is usually not an issue in this type of modeling. Instead, we're starting from CAD. It looks at what's there, but it looks at how to build it. And that's what CAD is. It's how do you construct the system. Okay, how do you build this problem? And as we saw with BIM now, you don't just know how to build it, but you also have a lot more properties of the system where you can watch it, how to maintain it. You could build. BIM is not something that you just build it and then you throw the drawings in a drawer someplace and forget about it. But instead, it's a live thing. You can keep track of maintenance events. You keep track of where manuals are and stuff of that sort. And you could maintain the system and not just use the system to build it, but also to maintain it. And now we're evolving to is, as Steve mentioned, we're going to the cloud, but we're also looking at not just how to build the system, how to maintain it, but also how to operate it. And that's, I think, where the evolution in the state of the art is. As we're going to actually being able to operate the buildings. We see this with pump stations already, but we're seeing this evolution now to cloud-based complete operations of the system, where the model now really not just looks like the real system, but it acts like the real system. And that's the next level as we're evolving to. Okay, so now we're going to talk about, this is a potpourri kind of talk. One of the issues that didn't get addressed in last month's talk on premise plumbing are fire sprinkler systems. And this is the one area of buildings where I do have some background in. And in most big buildings, the fire sprinkler system is separate from the domestic plumbing, and it's not really much of an issue. You can just that's done by fire sprinkler designers. But we're seeing now, especially in individual residences, are multi-purpose systems, where the sprinkler piping and the water use piping are the same pipe. And it saves a lot of money this way. You don't have to run 2 pipes through your house in order to have fire sprinklers and water for your sinks and washing machines. And this now has changed the way the systems are sized. So a lot of the stuff we saw in last month's talk kind of doesn't really apply here once fire sprinklers get involved, and you also have to consider that. So you have 2 different designs you have to really do for the same pipe. National Fire Protection Association has their standards, which are generally the guidelines, at least in the US, on how to put in these systems. AWWA also has this guidance document, which is what I'm showing you, the picture of the cover, that talks about this from the water distribution, water supplier system side of things, and looking at the water distribution aspects of it from a hydraulic engineer standpoint. And here's just a kind of an interesting picture I'm just throwing in to show you what the water quality can look like in some of these sprinkler systems. The one on the far right is when they just opened up a fire sprinkler and took the first water out, and they took samples along the way. And you can see that you don't want to have cross connections between separate sprinkler systems and your water system, because you get some really nasty looking water that's been sitting in a cast iron pipe for 20 years. It's going to look really bad. So you've got to decide, either are we doing a separate sprinkler system and domestic plumbing, or are we doing together so we keep the water fresh? We don't have that nasty stuff. Now we're going to move out of the building and looking at some of the other considerations. Now, how big is the lateral that takes the water from the water main in the street and takes it to the house? Is that really an important consideration? Well, I have a son who lives in South Philadelphia, and in South Philly, in the street that he lives on, you can basically stand in the middle of the street, reach your arms out in 2 directions, and you can touch the houses. There's such narrow streets, so the laterals aren't really all that important. On the other hand, we have places where you have these McMansions where the house is 100 feet back from the water main, and the things that happen in terms of head loss, water age in the service lines become important now. They're not just, the water moves instantly. You know what's going on in the main, then you must know what's going on in the building. Well, that's not really true. And there actually could be more head loss in the laterals, meters, and such than there is in the entire premise plumbing system. So you need to account for this. We just can't assume that the pressure in the main is that in that building. And it depends on the location, of course. Now, metering is becoming interesting because as research is being done, we have the water demand calculator and such. We see that we could downsize a lot of meters. A lot of meters are oversized in water systems these days. But when you downsize them, you're including extra head loss. So you've got to be able to account for that when you're looking at the system. And the big one, though, is when you have to do backflow prevention. Now, this is usually the biggest head loss of all. If you're going from the water main into the faucet or your shower, it's the backflow preventer if they're required in your system, because usually the minimum head loss is 10 psi through a backflow preventer. So you've got to be really careful to understand this when you're doing building design. And don't just say, okay, I know what the pressure is going into my building. Well, you better take into account all of these things. Now, AWWA has a manual, M22, that is coming out with the 4th edition now, which is for Peter Meyer, who comes to these sessions a lot, was the mastermind behind the latest edition. And I actually do the chapter on service lines, and that doesn't change because hydraulics doesn't change at all. But the metering and sizing one is really been something that's very different now. So if you get this manual will be out really soon, and I keep hearing that. And we're going to have a new edition, and I'd advise you if you're working in this area to get it, because it also documents the water demand calculator that Steve Buchberger and others put together, and it's the evolution of the state of the art in how to size these lines. So you can't just go from the main and assume what's going on in the water main is what's happening in the building. And this is one of the big questions that comes up is, when people are designing buildings, is what's the pressure in the main? I'm going to use that as a starting point for my model. And this always scares me when somebody asks me that kind of question, because there is no value. It may be 58 psi if you go out there and check it today. Tomorrow, maybe 45, or 2 o'clock in the morning, it may be 71. Or maybe 5 years from now, when there's growth, it may be 38. Or they may move a pressure zone boundary. It can change. And this is one of the real challenges in more so even in fire sprinkler systems, but also in building plumbing, is what do we use as the source pressure? We had this year, or this past year, we were supposed to have a joint session at the AWWA NFPA conference discussing this and how hard it is to get that boundary condition for these models. What is the pressure in the street? And also, if you're doing water quality modeling, what is the chlorine concentration? So we had a whole session to talk about the issues and how this isn't really a trivial issue. Because if you're very conservative, then you've got to put in a lot in your assumption about source pressure, then you got to put in bigger pipes. Or if you're not conservative, then you could put in smaller pipes, but it may not work if the pressure drops. So there's a lot of, knotty issues in this sort of thing. Moving along, the next topic is what happened. We're especially seeing this during the pandemic year, is what happens when there is stagnation in the system. At last month's session, we talked about the impact of pipe sizing on water quality and the premise plumbing, but it's also very important to understand what happens when you don't have water use. And there's a really good paper in AWWA Water Science about this that I'd refer you folks to. But what's important, though, last month's session, we talked about the impact of pipe sizing on water age. But the big thing that affects water age is occupancy. What is going on? How much water is being used? Like an example I use is the line in my house going to the laundry room. 6 days a week, that water keeps getting older, older, and older, and it changes. And the day you start the laundry, within a couple of seconds after you turn on the washing machine for the first load, the water's got really good water age. So so the effect of the size of the pipe going to the laundry room isn't really that great, as much as it is when are you doing the laundry. And a similar thing we have with schools during the pandemic. What do you do or hotels that don't have much occupancy during the pandemic? There's been some really serious issues and a lot of good work going on in that area. Guest bathroom in your house. We had 3 kids that have now grown, and the bathroom that they shared, there's always water being used there. And now that water doesn't even go to that hardly at all. The interesting situation I got involved in once was I was at a place where they were complaining about the odor in the restrooms, and it was the off season and no one was using the restrooms. And why did these restrooms stink? So what do you think caused that? Well, what I told them to do is go to every sink and just run the water for 20 seconds in the sink. And that solved the problem. Well, why did that happen? Well, it's because the traps dried out. If you have a long enough period with no water use, the traps dry out. And if you have the right meteorological conditions, that just sucks sewer gases from the sewers up into your building. And so these things where you don't have water use become, pretty interesting. Now, what's driving this thing? Strictly speaking, the Safe Drinking Water Act says you have to provide water quality at the tap. That's the principle. But the only thing where we really see much enforcement is in terms of lead and copper. I don't know if I've ever come across somebody, some water utility getting a notice of violation because of color or taste or something like that, because the regulatory folks don't really seem all that interested in anything beyond lead and copper, at least in the United States. Now, there's probably somebody in EPA will correct me and tell me about where they are enforcing it, but I don't see much effort. On the other hand, in China these days, they have some really serious issues in some of their high-rise buildings that they're building, and they're working on regulations where the water utility really has to make sure the water is good at the tap. And we're getting involved with some studies in China along those lines. And this is due mostly in some of their high-rise buildings they have there. And some of these buildings, in the old days, their buildings always had rooftop tanks because the water supply was not reliable. And now China has become much more modern, and they have very reliable supplies, but they still keep the rooftop tanks. And this is a place where the water quality can deteriorate. Here's just an example from one of the presentations we saw from China about what the building looks like. And it's kind of a cute drawing I thought I'd just share with you. I mean, this is actually, though, this cute drawing really looks like this in reality. So it's a lot messier, the system. And we've been playing around with some 3D plumbing. This was just a very crude model of multi-story building and some of the things you can do with modeling within that sort of thing, and looking at plumbing in 3D. So it looks like I was able to cut down enough slides that I was able to get my talk through without Bill shutting me off. So let's just summarize the take-home lessons. One is that there's a lot more to piping in buildings besides sizing pipes based on fixture units. And we have seen this evolution from CAD to BIM, nowadays going into digital twins. And we can now model things like pressure, velocity, water age. We couldn't. But it's important to consider the laterals, the meters, backflow, especially in terms of the head loss, but also in terms of water age. Fire sprinklers can have some interactions with the premise system, depending on where they split, whether you run the fire sprinkler system through the meter, whether the fire sprinkler system is a separate service line, or whether it's a multi-purpose system, becomes a real issue. And finally, the existence of tanks in buildings is another twist that you can model and study in premise plumbing. So that wraps it up for me. I hope this was useful, and I know we're going to have some hopefully questions at the end that we can talk more about this, because there are probably some people that want to argue about it. But I'll shut off my screen share and turn things back over to Walter.
Thank you, Tom, for a very interesting discussion. As I mentioned at the start, Phil Woolhouse will not be able to join us. He has some health issues, and it's the middle of the night in Australia. But he has an important message, so I'm just going to summarize 4 of his slides as a lead into our following speaker. Phil's going to talk about modern water hammer, a silent detriment to the premise plumbing system. Next. And as we're all aware, I think water hammer, also known as hydraulic shock, pressure transient fluid hammer, is defined as a pressure surge or wave caused when a fluid is subjected to a sudden change in velocity. Phil has been very passionate and worked over the last decade in this area, and has gone out and he's monitored at very fine scale water pressure in premises, and really has reduced it almost to a science. And next slide. And his takeaway message is, why is water hammer now silent? Increased use of acoustic absorbing materials, flexible tap connectors, polymer or plastic pipes. So the noise may have gone, but the damaging pressure shock has not. And so it is an important concept that must be viewed both in design and in analyzing water systems. Next. His takeaway message, how do we solve it? Consider water hammer at design, eliminate entrained airs, design and installation of surge protection, reduction in use of fast closing valves and equipment, correctly size and commission booster pumps, install plumbing system monitoring, identifying pressure spikes and issues as arise, and increase preventive maintenance. So it is an ongoing issue that we need to address. And in our following talk, Ben Kaiser is going to talk a little bit about modeling transient in premise plumbing. Ben is with AFT in Colorado, which is a specialized modeling company. And he's going to talk specifically about modeling fluid dynamics, temperature change, and transients in premise plumbing. Ben.
Good morning, everyone, and thank you for listening in and for inviting me to be a part of the webinar. And again, my name is Ben Kaiser, and I'm with Applied Flow Technology. We've been a global leader in the flow analysis software industry for over 28 years, and our software is used by thousands of engineers all around the world. And we develop products that provide analysis for liquid, gas, and slurry piping systems, steady state, and transient. And so I'll be talking about modeling the fluid dynamic behavior more in general. And so I'll show a demonstration of a few different piping systems and just focus on the fundamental hydraulics because some of the case studies that I'm showing isn't necessarily a water system specifically, but you'll definitely get the picture of the importance for doing flow analysis. And that's what I'm talking about today. And so it's really important to take a system approach in your piping system to help improve reliability. And one of the benefits is that you have a much better understanding of your complicated system and how your various components can interact with each other. And a lot of times during the design stage, components are designed without considering system interactions, and that can lead to various issues. Also, when your requirements or your operation changes at different times, those impacts are, may not always be fully explored or well understood. And so this can lead to several issues such as poor system performance, maintenance issues, high power consumption and energy costs, maintenance costs, product losses, loss of profit, things like that. And this is a really useful diagram called a Behringer curve, which basically compares a relationship between a pump and its reliability. So as you can see, there's several lines on here. We've got the pump curve itself, and then we have the efficiency curve. And then on top of that, we've also plotted what's called the reliability curve. And the goal is to ensure that your pumps are operating as close to the best efficiency point as possible. And the more that you can operate close to that location, the more that you're going to be avoiding these types of problems if you're riding back or forward on your pump curves. And so there are various standards available for allowing, your pump to operate within various proximity to the best efficiency point. One of the standards is 20% less than the BEP or 10% above the BEP, and that's a preferred operating region that you'd want to stay within. So if you're able to operate your pump at the best efficiency point at all times, this is known as one mean time between failure, which is just a very qualitative approach to understanding how the reliability of your pumps will be able to be maintained. If you were to operate at the boundaries of 20% to 110%, or I'm sorry, 80% to 110% of the BEP, that reduces the average time between failure by half. So the further and further away that you get from operating at your best efficiency point, you're going to be experiencing several other issues, and that decreases the amount of time between failures significantly. So you want to try and stay within this region as much as you can, and that's where flow analysis is really beneficial, because you can model all sorts of different cases and really get a much better understanding of how your components interact with each other, and explore what it looks like when your system requirements or if your operation changes. So when you're building a hydraulic model, this is very similar to the previous speaker, I believe, Tom, when he was mentioning about hydraulics. And so this is just echoing that. If it's in the system, it's included in the model. And so really important to account for all your proper fluid properties, densities, viscosities, etc. Pipes, again, you're going to need the inner diameter to be able to calculate the hydraulics. And then the wall thickness is also important if you're doing heat transfer modeling or if you're doing water hammer analysis. Friction models can be different. Insulation and elevation changes, all of those things need to be captured for your piping. Your boundary conditions for tanks and liquid levels, pumps with your head curves, efficiency, your power curves. MPSH is really important to pay attention to. If you have less MPSH available than that which is required by your pumps, then you're going to be cavitating your pump. Definitely a situation you want to be sure to avoid. And then when you're doing a hydraulic flow model, keeping things a bit more simplified is certainly a good practice to take. And so a lot of times if you're trying to model complex pieces of equipment, simply specifying the pressure drop versus flow profile as a resistance curve is a really good way to capture the hydraulic losses through those devices. So keeping it simple will help you get a quality flow analysis. Valves, you can include your CVs or K factors, open percentage data. And then, of course, don't forget to include your fittings. K factors or equivalent lengths can be modeled to include all of your minor losses. And this is what a hydraulic model might look like. So we have a cooling tower system where we have a basin where the flow starts. Then we have 4 pumps operating 2 separate trains in parallel, and they flow through a series of heat exchange devices. There are some crossover lines where if you need to transfer fluid from one train to another by shutting these pumps off, you can do that. And that's one of the beauties of doing flow analysis is you can work with all the different what if types of analysis where you're modeling different operating cases. So this is a graphical picture of what the model of the system looks like. And then here's an example of the input for the piping system. So we've got the pipe lengths, some minor losses that we've included with the pipes itself, the material size, etc. And this is not showing every potential input parameter for the piping, but with flow analysis software, you can easily add and remove parameters that you care about at will. And then an example of what the output might look like, there's tabular formats. It's important to pay attention to how your pumps are operating. And as you can see for this particular system, the pumps were sized very well for operating right at their best efficiency point. And there's plenty of MPSH available, and that's something that you would focus on. You can see the individual results for the flow rates and velocities and pressure drops in each individual pipe run itself. And then doing profile plots is also helpful to be able to examine how your pressure changes throughout your system over the flow length. And so this is just demonstrating what the pressure change throughout a flow path would potentially look. And we get the boost in pressure from the pumps. We have a significant pressure loss across one of the heat exchangers, so on and so forth. So that's just a very basic example of what a flow analysis model might look like. Now, how do piping systems or how do pumps become inefficient? There's several things to just keep in mind. There's a decent lack of standards for designing pumping systems where the engineers can choose how they do a flow analysis, or if they even want to do a flow analysis. And if they're not specifically asked to, then there's less motivation to do it. And when that happens, it's quite possible to oversize pumps or valves, other pieces of equipment, and that can cause problems. Systems designed to meet future requirements may only be operated to hit current needs, and so that can throw a wrench into things. As they talked about for the previous speakers, system ages, and that certainly affects the water quality, which is really interesting for me learning about. But it's going to have a buildup of corrosion inside the piping, and that will scale down the inner diameter and will increase the pressure losses. So it's important to evaluate that. And then whenever the process changes or modifications, those different changes can affect your system operation. So when you look at a system-wide approach, you can get a much better handle on what's going on, and it's better to focus on that system approach up front rather than spending lots of money fixing and operating systems that just continually have issues. Now, I'm not going to spend too much time on these bullet points. I have provided the slides, and so you can take a look through. These are just some different cases that you would look at with flow analysis software, different operating conditions, water hammer, gas flow is really important to evaluate. And so these are just some important points to keep in the back of your mind. And here's a list of all sorts of different things that you can do with flow analysis software. I want to talk about a case study that's interesting here really quick. It is for a raw brine injection system for an oil and gas facility. And essentially they had 5 vertical pumps and 5 horizontal pumps operating in their plant. And the goal is to displace product in the chemical plant's underground storage facility. And the pumps competed hydraulically with each other, and many of them were operating very far from their best efficiency point, down to 20% to 50% of BEP, and obviously that caused some major issues. 41 repairs over 5 years, about $1.25 million, and mean time between failures was just under 15 months. And this is a link to where you can see the case study for yourself. And so this is a basic hand sketch of what their system looks like. And when they fully built everything out, this is their fully built model. So nice and complex, lots of branching and flow splits and loops. And again, their pumps are operating very far away from BEP. So the vertical pumps are the ones that were having the problems. Horizontal pumps, not so much. Those weren't really an issue. And this is a crossover valve that they were experimenting with, turning or closing that valve to see if they could improve the pump performance. And then this is the cavern that they're delivering the flow to. So they looked at several different scenarios where they tried keeping all valves open. They tested closing that crossover valve, and then increasing or maintaining a cavern pressure of 300 psig, and this is the entire scenario tree of what they were doing in their analysis. So this is an excellent way to be able to really see what's going on in all of your different what-if types of questions that you have. So I just want to focus on two of the test scenarios, test 4 and test 7, and give a quick example of what that looks like. So for this comparison, they've closed off the crossover valve. As you can see right here, there's no flow going from through that line. And then they changed the cavern pressure to 300 psig. And this is where they're operating 4 pumps in parallel versus operating only 3 pumps in parallel. And they're able to get some incredible improvements in BEP. So with operating 4 pumps in parallel, these 3 pumps were operating at about 55% of BEP. Simply by just shutting off 1 pump, they were able to get the flow rates that they needed for the proper delivery, but their BEP proximity jumped up by 15%. So that was a significant increase, and in the end, they're able to get much better operation after doing the analysis. So here are all the different test scenarios that they looked at, and they're able to still maintain the required flows the system needed, and better flow paths and pump operation helped reduce those failures that they continually were seeing. So now a quick shift from focusing on the hydraulics to also paying attention to the heat transfer in the system as well. And the thermal analysis is really important to account for how the temperature changes throughout the system. And this is just an example of a network where we have a cooling water loop modeled on the left-hand side, and then a hot oil circuit on the right-hand side. And these two heat exchanger objects actually represent the same physical heat exchanger in the flow model. So the cooling water network, the cooling water flows through the tube side, while the hot oil flows through the shell side. And we've got a couple of valves here that can be tuned to change flow rates or temperatures. And so this system just gives it an example of accounting for convection through the piping system, layers of insulation. You can model the heat transfer through the heat exchangers, and it just goes to show where modeling your thermal analysis is just as important as it is for capturing all of the hydraulics. All right, now let's talk about transient modeling. There's 2 different types of transient analysis that you can do, and I like to call it long-term versus short-term simulation. So a long-term simulation is non-water hammer and non-surge related. This is where you're doing a simulation for several minutes, hours, perhaps even days, and you want to see how the system dynamically interacts over longer periods of time. And so some really important assumptions that essentially every step is at a steady state operation. It's ignoring the wave speed and not tracking the pressure and velocity wave propagation in this type of transient analysis. So this is valid when you're running your simulation for long periods of time. If you have a simulation of 10 minutes and your time step is every minute or so, then that could be a valid assumption. And it might be where all the pressure waves have dampened out between time steps in that case. The short-term transient simulation, this would be a water hammer or surge type analysis. And so the simulation periods are going to be much shorter, several seconds to a minute. Maybe you want to capture what happens a few minutes after your transient event happens for the sudden upset in your system. So this is going to capture what happens immediately after a surge event, and it will account for the proper wave speed in order to determine how the pressure and velocity waves propagate throughout the system. So here's the types of questions that you might look at for doing a long-term simulation.
Sorry to interrupt. You have about 3 minutes remaining.
Oh, perfect. Thank you. So here, how does the system change over long periods of time? How do your control valves respond if you're changing from one operation to another? Where do your pumps operate on their curves as the daily flow demand changes? These are all different questions that you'd want to take a look at when doing your long-term transit analysis. Tank filling and draining is a really important one. What causes a valve to close? Do we reach a certain liquid level that we need, or is the tank about to overfill? So I'm going to demonstrate a quick example of I'm sorry. Not the example yet. I'm showing the questions that you would ask for a water hammer simulation first. So here, what happens when the valves actually slam shut? How high do the pressures get? Do you have cavitation in your system? What are the pressure magnitudes when your vapor bubbles collapse? Different things like that. And so these are all important questions to keep in mind. And surge suppression equipment is important to pay attention to. And this is a very simple example of a tank filling application. So initially the tanks are empty and we have our valve that's initially open, and there's two reasons that the valve might close. One is that both tanks might have reached their required level, or either one of the tanks potentially gets close to overfilling. So there's logic that I set to shut off the valve at 27 feet. So there's two cases where we need either 15 feet or 20 feet in the tanks. And the questions are, when do the valves close? What causes the valve to close? And to track the changes for the tank liquid heights, flow rate, and pressure at the valve over time. And it's just a simple 3-minute simulation with 1-minute time steps. So here's the results for the first case, where our goal is to fill each tank to 15 feet. And as you can see here, both tanks meet their desired liquid level of 15 feet. They stay below that 27-foot threshold. And because the second tank, this meets the liquid level later, that's when the valve starts to close. And then once the valve is closed, we see a deadhead pressure of 125 psi. Is that actually what the pressure is going to be when our valve closes? Now, I'm not going to spend too much time on the second case. The main thing to see here is that when we simply want 20 feet in the tanks instead of 15, well, the second tank never reaches the 20-foot desired level, and the first tank is about to overfill. So that's what causes the valve to close in that particular case. And so this is where the water hammer simulation begins. So once the valve is slammed shut, when you do the water hammer analysis, this is going to demonstrate how the pressures are actually changing throughout the system by accounting for the acoustics. So the red line is for what it looks like if we close the valve in 5 seconds, and the blue line is what it looks like if we close the valve in 10 seconds. And this is part of the water hammer analysis to determine how long should you close the valve to reduce the pressure surge that you would see in your system. So that's what I have for today. Thank you very much for your time. And if anyone has any questions, feel free to contact me and I'll be glad to help.
Our final presenter is Bram Hillebrand, who is with KWR in the Netherlands. Bram works with Miriam Bloker, who has given several presentations on this webinar series. Bram, provide.
Well, as said, I am Bram Hillebrand. I work at KWR Water Research Institute, which is the water research institute of all the Dutch water companies. And I will be presenting something about temperature modeling in premise programming using EPANET multi-species extension. And this is work done by me, by Mirjam Blokker and others at KWR. So first of all, why would we want to model temperature in a premise plumbing system? Well, as we all know, that stagnant warm water might lead to additional biological risks, and therefore Dutch law, but I can imagine other laws as well, require temperatures to be less than 25 degrees Celsius, which is about 77 degrees Fahrenheit. So this is why we'd want to model the temperatures in a premise plumbing system. So what influences are there on water temperature at the tap? Well, of course, there is the initial water temperature. So that will be the temperature of the water leaving the distribution net. But on top of that, there is environmental temperature. So that will be the air temperature within the house or the soil temperature surrounding the connection pipe. It is the pipe flow regime, the residence time, as we already saw, which of course depends on the consumption pattern. But also things like the material of the pipe, is it copper, is it plastic, the length of the pipes, the layout of the premise plumbing system, and also importantly, what this we focused on is the position of other warm water pipes or other possible heat sources. And this all influences the water temperature at a certain point in time and space. So, APANET MSX, as you might know, is the multi-species extension on top of APANET. And you can also use this to model temperature in a distribution system, and in this case, a premise plumbing distribution system. So temperature changes both in time and in space. And the spatial temperature change is driven by advection, and that part is calculated by APANET MSX. But we can also use MSX to calculate the temporal temperature change, which is governed by this equation, where this term, and especially the heat trend coefficient, is different for pipes which are located in soil and pipes which are located in the air, and it's also different for horizontal and vertical pipes, which I will show on the next slides. So, the heat transfer coefficient is of course a summation of the different heat transfer coefficients for the wall, the water, for outside, and it can be summed up in this fashion, as it is reciprocal to the thermal resistance, which is shown here. And in this case, of course, the heat transfer coefficient for outside is either the heat transfer coefficient for the air or for the soil, depending where the pipe is located. The heat transfer coefficient for water depends on the Nusselt number for water, and that in itself again depends on the Reynolds number, which is calculated by APANET. Formulas for that are shown here. So that's something that APANET gives us. So if we move on to the heat transfer coefficient for air, which you can see on this formula, is that it is dependent on the Nusselt number for air, and that is different for horizontal and vertical pipes, because it is dependent on the Rayleigh number for air. And you can see the formula for the Rayleigh number for air is given here. And then this last term, this D, that would be the inner diameter for horizontal pipes, but for vertical pipes, it would be the length of the particular pipe. So this is considerably different, and therefore important to take into consideration. But if you do this, if you take this all into consideration, then you can substitute this term with the previous formulas, and then we can add this formula as a rate to the pipes in the MSX files, as is shown here. And then we define T-water as a species in the MSX files, and we can add some boundary conditions at certain nodes, for instance, at the initial water temperature from the distribution line as it enters the system. And what is also important is that we then, at the parameters, we indicate whether a pipe is in the air or in soil and whether it is vertical or horizontal. We can do this by zeros and ones, and then this KK factor, which is this factor of the formula, we can multiply that with these zeros and ones, and then in each case use the correct version of the formula for horizontal or vertical and air and soil. So onto a case study that we have done in the past year. So using this temperature modeling in IPANET MSX, the case study investigated the influence of district heating on the temperature of the drinking water in the connection pipe and throughout the rest of the domestic drinking water distribution system. In this case study, we considered that the soil temperature was constant and that it was heated up due to the proximity of a district heating connection pipe. And especially in all the parts of Dutch towns and cities, this is a risk because the space between the distribution lines and the houses tend to be limited, and we have increasing use of district heating due to the energy transition. So I'll show some model setup. So I'll start here on the right. Here on the right, I show the in the blue we show the drinking water connection line, and in red is the district heating connection line, which are in close proximity of each other. The district heating connection line has a constant temperature, which will heat up the soil around it and also the soil around the drinking water connection line. And then within the house, the system looks very simple. We have a kitchen tap, there is a toilet, some shower, bathroom tap, another toilet, and a washing machine. And the yellow lines show the warm water pipes. So in a model setup, it would look like this. So we would do the pattern modeling using SimDame, which was presented, I think, last month at least. And with this, we can create individual tap patterns for each tap unit, and also separate the cold water from the warm water. So we would get a cold water only tap pattern for the shower, for instance. Then, as I showed on the previous slide, we can do this temperature modeling using the temperature differential equations into putting that into MSX, and together with the tap patterns and a hydraulic model, IPANET model representing this house, we can use IPANET to calculate some results. So this is what we did. First, I will show the heating of drinking water in the connection pipe. So this is when there is no flow is happening. So for instance, during the night. And what the graph shows is that water will heat up in roughly about 20 minutes to the soil temperature, which in this case is 30 degrees Celsius or 86 degrees Fahrenheit within 20 minutes. So the curves are slightly different for summer and winter, which has an influence on the initial water temperature. But still, in both cases, we will reach this maximum temperature rather quickly, and the material of which the connection pipe is made, which copper or PE in this case, which is the two most common ones in the Netherlands, do not really have any effect on the speed or the maximum temperatures that are reached within in the connection pipe. So what does this mean for the water entering the house itself? So what I show in this graph is the water temperature at the water meter or the end of the connection pipe, and the water temperature at the shower. And this is while the shower is flowing. It's a winter example in this case. And what is important to remember that this is the temperature of the water if we were only of the cold tap. So it is the temperature of the water that we would get if we were taking a cold shower. I will walk you through the graphs themselves. So we start with the orange one, which is at the water meter. So as soon as the shower is turned on, there is water flowing through the water meter, which is coming from the connection pipe. This was heated up because of warmer soil temperatures to about 30 degrees, and that's also the 30 degrees Celsius or 86 degrees Fahrenheit, and that is also the temperature that we see at the water meter. It's about 1 minute, 1.5 minutes. That of course depends on the length and the diameter of the connection pipe, but in this case it's about 1 minute of water, and then the temperature drops to about 13 degrees Celsius or 55 degrees Fahrenheit, which is already about 3 degrees Celsius warmer than the temperature of the water it had in the distribution net, meaning that the short time it spent in flowing through the connection pipe, it already warmed up about 3 degrees Celsius. So, and then the temperature we see after that is constant because the water entering the connection line is from the distribution net is constant, and the heating up is also constant. So at the shower, the temperature profile looks like the blue curve. So initially we get a pocket of water of about 20 degrees Celsius or 68 degrees Fahrenheit. This is the water that was in the distribution net within the house, somewhere between the water meter and the shower, and it has been heated up to room temperature, which was 20 degrees Celsius in this case. After that, the warmed up pocket of water from the connection pipe comes to the shower. As we can see, somewhere between the water meter and the shower, it cooled down about 1 degree Celsius, probably. So a little bit, but not that significant. So it's still about 27 degrees Celsius or about 80.6 degrees Fahrenheit when it reaches the cold tap of the shower. Again, this is about a 1 minute, 1.5 minutes, which is dependent on the length and diameter of the connection pipe. And after that, the colder water, which comes directly flowing from the distribution line, reaches the shower, and reaches the shower at about slightly below 15 degrees Celsius or 59 degrees Fahrenheit. And so again, so somewhere between, as this is the same water that flew for the water meter at this time, we can see that it is roughly still about an extra 2 degrees Celsius heated up somewhere between the water meter and the shower, which is simply due to the room temperature surrounding the pipes. So what we can see, what this plot shows is that the temperatures or the maximum temperatures that end up at the shower or any other tap for that matter, as long as are almost completely dependent on the temperature of the soil surrounding the connection pipe, which in this case was 30 degrees Celsius. But if that would be hotter, the water pocket would be hotter. If that would be colder, then the water pocket would be colder. And within the distribution system within the house, water tends to cool down a little bit or warm up a little bit, depending on its starting temperature, but not as significant as the water as it does in the connection pipe itself. And if 30 degrees Celsius or 86 degrees Fahrenheit would indeed be a correct soil temperature, then this might pose extra biological risks as the water can be stagnant in the connection pipe for quite some time, and it then is there at 30 degrees Celsius for quite some time. This is what I wanted to show. I think I went a little fast, but that leaves more time for questions. So thank you all for your attention.
Thank you, Brandon. In fact, thanks all of our speakers. We have reached the end of our hour and a half. There's been some very interesting discussion in the chat room, and you can take a look at it there. But I think we will cut it off here, and I'm sure there are a lot of questions people still have. Bill, would you like to do a wrap up on where we're going?
Yeah, sure. So again, thanks for joining us. If you are not part of our regular mailing list and would like to join the list, please reach out to Jun Suk, and who's the committee chair, and he can add you to the list. And finally, we have our final webinar in this webinar series coming up next month. It's looking to the future, which will be led. It'll be a sort of a joint effort by the entire task committee here. It'll be April 26th from 10 to 11:30 Eastern. So we hope that you can join us for that, and we'll be going sort of wrapping up the whole webinar series and telling you what's next for the committee and what the webinars might be in the future. So I think that's it. Thank you all.